Welcome to Lecture 7 of Geometric Physics 1. Today is called Symplectic Manifolds and Darboux's Theorem. The reading is Marsden and Ratiu, Chapter 5, with Frankel on phase space and the Poincaré 1 form. For next time, read Marsden and Ratiu, sections 6.1 through 6.5. Today, the symplectic form finally lives on a manifold, and the machinery of 6 lectures gets spent, most of it in 3 lines. Lecture 5 gave us Cartan's magic formula, the Lie derivative along x equals d after the interior product with x plus the interior product with x after d. Lecture 6 did the linear algebra of a symplectic vector space. Today, those two meet on a manifold. There are 6 stops. First, the definition, a 2 form that is closed and non-degenerate with the 2 conditions motivated separately. Second, the count. Symplectic manifolds are even-dimensional, orientable, and carry the volume omega to the n over n factorial. Third, symplectic transformations and the group they form. Fourth, Darboux's theorem. Fifth, the equation defining the Hamiltonian vector field, and the 3-line proof that its flow preserves omega. Sixth, Poisson brackets, conservation of energy, and a first look at Noether. The center of the hour is Darboux. Symplectic manifolds of equal dimension are indistinguishable near any point. There is no symplectic curvature and no local invariant of any kind. Every symplectic question with a non-trivial answer is global. First, the objects themselves, a closed non-degenerate 2 form on a manifold, and the examples that make the definition worth making. A symplectic manifold is a pair, a smooth manifold P and a 2 form omega on it, subject to 2 conditions. First, d omega equals 0, so omega is closed. Second, omega is non-degenerate at every point. Non-degenerate means this. If omega of v with w vanishes for every w in the tangent space, then v itself is 0. Equivalently, the map sending a vector v to the interior product of v with omega is an isomorphism from the tangent bundle onto the cotangent bundle. We call that map omega flat. The 2 conditions are of completely different kinds, and it is worth saying so out loud. Non-degeneracy is pointwise linear algebra. It is a non-vanishing determinant, an open condition, exactly what Lecture 6 imposed on one vector space, now imposed at every point at once. Closedness is a differential equation on the coefficients of omega. It is the only differential equation in the whole subject. One footnote. In infinite dimensions, the 2 readings of non-degeneracy come apart. Injective is called weak, bijective is called strong, and Marsden and Ratiu's field theory examples are only weak. In finite dimensions, there is no difference at all. Why insist on non-degeneracy? Physics hands you a function h. Dynamics needs a vector field. Something has to convert one into the other, and the converter is omega flat. The Hamiltonian vector field xh is the inverse of omega flat, applied to dh. This is the job the metric did back in Lecture 3, done by a different tensor. A metric is symmetric, a symplectic form is antisymmetric. Under the metric, a function becomes its gradient. Under the symplectic form, the same function becomes its Hamiltonian vector field. The last row of that comparison is the one that matters. The gradient is orthogonal to the level sets of the function. The Hamiltonian vector field is tangent to them. Feed xh into its own defining equation. Then dh applied to xh equals omega of xh with xh, and that vanishes because omega is antisymmetric. So here is the thing to keep. A metric turns a function into the direction of steepest ascent. A symplectic form turns the same function into a field tangent to its own level sets. Conservation of energy sits in the antisymmetry of omega before any equation of motion is written. Non-degeneracy alone would already give us Hamiltonian vector fields. Closeness is what makes them behave. 4 answers, and each is proved today or was proved already. 1. It is free, where symplectic forms actually come from. On a cotangent bundle, we set omega equal to minus d theta back in Lecture 3. So d omega is minus d of d theta, which is 0. Nobody imposed it. 2. It is what makes flows canonical. By Cartan, the Lie derivative of omega along xh is d of the interior product of xh with omega, plus the interior product of xh with d omega. The first term is d of dh, which always dies. Only closedness kills the second. 3. It is the Jacobi identity. Given non-degeneracy, omega is closed if and only if the Poisson bracket satisfies Jacobi. 4. It is the integrability condition behind Darboux. A non-degenerate 2 form is closed exactly when it has constant coefficients in a chart around each point. 2 conditions, 2 characters. Non-degeneracy is algebra imposed pointwise. Closedness is the single differential equation of the theory. Nearly everything today is a corollary of one or the other, and it is worth tracking which. 2 examples we already own. The first is the model. Take R2n with coordinates q1 through qn and p1 through pn, and let omega naught be the sum of dqi wedge dpi. It is closed because the coefficients are constant and non-degenerate by lecture 6. This is the manifold Darboux says everything looks like. The second is every cotangent bundle. On T star q, we have the tautological one-form theta, and omega is minus d theta, which is again the sum of dqi wedge dpi. Closed because it is exact. Non-degenerate by inspection. Every configuration space generates a symplectic manifold with no further choices. No metric, no coordinates, nothing. Now notice something. On a cotangent bundle, omega is not merely closed, but exact, and that is a real restriction. Suppose P were compact without boundary, with omega equal to d theta. Then omega to the n is d of something, so by Stokes its integral over P is 0. But omega to the n is a volume form, so that integral cannot vanish. No compact symplectic manifold is a cotangent bundle. Now 2 examples that go beyond phase space. First, the 2 spheres sitting in R3. For tangent vectors u and v at the point x, let omega be x dotted into u cross v. Closed for free because a surface carries no 3 forms at all. Non-degenerate because it is an area form. Its integral over the sphere is 4 pi, which is not 0, so it is not exact. The 2 sphere is a symplectic manifold that is not any cotangent bundle. It is the phase space of a classical spin and a coadjoint orbit of SO3, which we meet in lecture 16. Second, complex projective n space with the Fubini study form, and therefore every smooth projective variety. Products work too. Given 2 symplectic manifolds, the product carries the sum of the pullbacks, and that is how the phase space of 2 interacting systems is assembled. Now the counterexample. The 4 sphere carries no symplectic form at all. On a compact manifold without boundary, the top power of the class of omega must be non-zero, so the second cohomology must be non-zero. For the 4 sphere, it vanishes. Being symplectic is a topological restriction, and lecture 4's de Rham cohomology is what detects it. 3 consequences of the definition, all at once. A symplectic manifold has even dimension, it is orientable, and it comes with a volume form. Even dimension is linear algebra from lecture 6. The matrix of omega equals minus its own transpose, so its determinant equals minus 1 to the dimension, times that same determinant. Non-degeneracy says the determinant is not 0, so the dimension is even. Write it as 2n. Orientability and the volume come together. In canonical coordinates, omega to the n equals n factorial times dq1 wedge dp1, and so on through dqn wedge dpn. That is nowhere 0, so it orients P, and dividing by n factorial gives a volume form. It is called the Liouville volume. Here's the point. A symplectic manifold carries a canonical volume with no metric anywhere in sight. Lecture 4 asserted that phase space always has a volume. This is the reason. And that volume is conserved by the dynamics with a proof at the end of the hour that costs 1 line. Now the maps between symplectic manifolds. Then the theorem that flattens all of them at once, and a short word about complex structures. A smooth map from one symplectic manifold to another is called symplectic, or classically canonical if the pullback of the target form is the source form. A symplectic diffeomorphism is called a symplectomorphism. 3 quick facts. First, if the dimensions agree, every symplectic map is automatically a local diffeomorphism. If the tangent map kills a vector v, then omega of v with anything vanishes, so v is 0. Second, the symplectomorphisms of a fixed manifold form, a group, The pullback of a composition is the composition of the pullbacks, and inverses work too. Third, symplectic implies volume preserving, since the pullback of omega to the n is the top power of the pullback of omega. So symplectomorphisms sit inside the volume preserving diffeomorphisms. A word on names. Canonical transformation is the older term, defined in the classical literature by preservation of the form of Hamilton's equations. The two definitions agree, and preservation of omega is the invariant one. So this group is the symmetry group of classical mechanics, and it is infinite dimensional. Lecture 8 shows that every change of configuration coordinates lifts into it. But the group is far larger than that. It contains every Hamiltonian flow as well. Here is the theorem. Let P with omega be a symplectic manifold of dimension 2n, and let Z be a point of P. Then there is a chart around Z that sends Z to the origin. It gives coordinates q1 through qn and p1 through pn, and in those coordinates omega is exactly the sum of dqi wedge dpi. Such a chart is called canonical or a Darboux chart. Restated, every symplectic manifold of dimension 2n is locally symplectomorphic to R2n with its standard form. All of them, near every point, always. There's a sharp converse worth carrying with you. A nondegenerate 2-form is closed if and only if it has constant coefficients in a chart around each point. So closed and locally constant are the same hypothesis said in two languages. That is the cleanest way to understand what the closedness condition was ever asking for. Now compare this with the situation for a metric, because the comparison is where the meaning lives. Set the two geometries side by side. For a Riemannian metric, the best you can do at a point is make the components the identity, plus terms of second order in the coordinates. The obstruction to doing better is that second order term, and that term is curvature. Curvature and its covariant derivatives are genuine local invariants. Two metrics are locally isometric when those invariants agree. For a symplectic form, the normal form is exact. Not to first order, not to second order. Exactly. There is no obstruction, so there are no local invariants of any order, and any two symplectic manifolds of the same dimension are locally symplectomorphic. The contrast is precise. A metric can be flattened to first order and no further, and the failure at second order is a tensor you can measure inside any small ball. A symplectic form can be flattened completely, so symplectic geometry has no local invariants. Every neighborhood of every symplectic manifold looks like every other. Every symplectic question with a non-trivial answer is therefore global. It is about the topology of P, or the fixed points of a symplectomorphism, or which balls embed in which cylinders. That is why the field is called symplectic topology. The proof is worth seeing because the method comes back. 3 steps. Step 1. A single point. By the linear normal form of lecture 6, choose coordinates centered at Z so that omega agrees with the standard form at that one point. Nothing holds nearby yet. Step 2. Interpolate on a small ball. Let omega t travel the straight line from the standard form to omega. Every omega t agrees with the standard form at Z, and non-degeneracy is an open condition. So on a small enough ball, every omega t is non-degenerate. Both ends are closed, so their difference is closed. By the Poincare lemma of lecture 9, that difference is d alpha, with alpha vanishing at Z. Step 3. Flow it. Solve for the time-dependent field xt whose interior product with omega t is minus alpha. Non-degeneracy makes that solvable, and xt vanishes at Z, so the flow exists near Z. Now differentiate the pullback of omega t along that flow. The Lie derivative term gives minus d alpha. The explicit time derivative gives plus d alpha. They cancel. That middle step is Cartan's magic formula again. Moser's trick is the standard weapon for theorems saying all such structures are locally the same. A short word on complex structures. An almost complex structure on P is a bundle map J from the tangent bundle to itself, with J squared equal to minus the identity. It is compatible with omega if two things hold. Omega of Ju with Jv equals omega of u with v. And the recipe, G of u with v equals omega of u with Jv, gives a positive definite form. Then the package is called almost Kähler, and Kähler if in addition J comes from honest holomorphic charts. the three structures are locked together. Any two of omega, g, and j determine the third. The metric is omega with j inserted in the second slot, and omega is the metric with j inserted in the first. Three facts to carry. Every symplectic manifold admits a compatible j, and the space of such j is contractible, so j is a tool you pick up when convenient, not extra data. The examples are complex n-space, complex projective n-space with the Fubini study form, and every smooth complex projective variety. And Kähler implies symplectic, but the converse fails. There are compact symplectic manifolds carrying no Kähler structure at all. Now the dynamics. A function on a symplectic manifold becomes a vector field, and its flow turns out to preserve everything in sight. Let H be a smooth function on a symplectic manifold. The Hamiltonian vector field XH is defined by one equation. The interior product of XH with omega equals DH. Written out, omega of XH with V equals DH applied to V for every tangent vector V. The manifold, the form, and the function together make a Hamiltonian system. XH exists, is unique, and is smooth. The proof is one line. XH is the inverse of omega flat applied to DH. Existence is surjectivity of omega flat. Uniqueness is injectivity, and both of those are non-degeneracy. Nothing else is used anywhere. Now put it in a Darboux chart. Write XH with components along the q directions and along the p directions. Take the interior product with omega, match it against DH, and out come two equations. The rate of change of Qi is the partial of H with respect to Pi. The rate of change of Pi is minus the partial of H with respect to Qi. Those are Hamilton's equations, and by Darboux, every Hamiltonian system on every symplectic manifold looks locally exactly like this. Here is the payoff. Let Ft be the flow of XH. Then the pullback of omega along Ft is omega for every t. Every time T-map of a Hamiltonian flow is a symplectomorphism. Watch the proof. The Lie derivative of omega along XH equals d of the interior product of XH with omega plus the interior product of XH with d omega. That is Cartan's magic formula from lecture 5. The first term is d of dh, which is 0. In the second term, d omega is 0. So the Lie derivative vanishes. So the time derivative of the pullback vanishes, and at time 0, the flow is the identity done. Each hypothesis is spent exactly once. Of dh being 0 is d of d is 0 from lecture 3, which is equality of mixed partials. The second term dies by closeness of omega, and non-degeneracy was already spent in producing XH at all. This is what lecture 5 was for. Cartan's formula converts a statement about a flow, which is an integral object, into a statement about two derivatives, which is algebra. The hardest theorem in a mechanics course becomes 3 lines. The corollary is immediate. Hamiltonian flows preserve the Liouville volume. Pulling back that volume means pulling back the top power of omega, and the pullback of omega is omega. So the volume of the image of a region equals the volume of the region. In coordinates, it is the vanishing of a divergence. Differentiate the partial of h with respect to p in the q direction. Subtract the partial of h with respect to q, differentiate it in the p direction, and the two cancel. That is the equality of mixed partials once more. Think about what this forbids. No asymptotically stable equilibria, no limit cycles, no attractors of any kind, because an attractor swallows volume. Damping is never Hamiltonian. And by Poincare recurrence, almost every orbit in a bounded region returns arbitrarily close to where it started. But volume is only a shadow of the real invariant. Preserving omega is strictly stronger than preserving omega to the n, as soon as n is at least 2. Gromov's non-squeezing theorem says a ball of radius r embeds symplectically in a cylinder of radius capital R only if r is at most capital R, whatever room the volume allows. Last section. The bracket, the one equation that replaces Hamilton's equations and the first appearance of Noether's theorem. Define the bracket of f and g to be omega evaluated on their Hamiltonian vector fields. Unwinding that gives equivalent readings. The bracket is df applied to xg, and it is also minus dg applied to xf. In any Darboux chart, the bracket is the familiar sum. Take the partial of f with respect to qi times the partial of g with respect to pi. From that, subtract the partial of f with respect to pi times the partial of g with respect to qi. The bracket of qi with pj is the Kronecker delta. The bracket is bilinear and antisymmetric. It obeys the Leibniz rule, and it satisfies the Jacobi identity. And here is the sharpening promised earlier. Given non-degeneracy, Jacobi holds if and only if omega is closed. One warning: books differ on the sign of the bracket and on the sign in the definition of the Hamiltonian vector field. Lecture 17 turns all of this around. Keep the bracket, its Leibniz rule, and its Jacobi identity, and throw the form away. What is left is a Poisson manifold. Every symplectic manifold is one. The converse fails, and the failure is where the rigid body lives. Along the flow of xh, every observable evolves by the bracket. The time derivative of f equals df applied to xh, which is the bracket of f with h. That single equation replaces Hamilton's equations. Take f to be a coordinate or a momentum, and you get them back. Energy first. Put f equal to h. The time derivative of h is the bracket of h with itself, and that vanishes by antisymmetry. Conservation of energy uses nothing about h and nothing about the manifold. It is the antisymmetry of omega and nothing else. Now constants of motion. A function f is conserved by the dynamics of h exactly when the bracket of f with h is 0. But that equation is antisymmetric, so it says equally that the bracket of h with f is 0. And that says h is invariant under the flow generated by f. That equivalence is Noether's theorem in its cleanest form. A function f is conserved by the dynamics of h precisely when the flow of f is a symmetry of h. Symmetries and conserved quantities are one list, read in two directions. Lecture 19 makes this systematic through the momentum map, and Lecture 20 uses it to reduce. 7 things from today. 1. A symplectic manifold carries a closed nondegenerate 2 form. Nondegeneracy is pointwise algebra, and it converts functions into vector fields. Closedness is the one differential equation, and it is what makes flows canonical and Jacobi hold. 2. The dimension is even, the manifold is orientable, and omega to the n over n factorial is a canonical volume built with no metric. 3. A map is symplectic when it pulls the target form back to the source form. The symplectomorphisms form an infinite dimensional group, sitting strictly inside the volume preserving diffeomorphisms. 4. Darboux. Every symplectic manifold is locally R2n with its standard form. No local invariants, no symplectic curvature, no local theory at all. 5. The interior product of xh with omega equals dh has a unique solution because omega is nondegenerate. In a Darboux chart, it is Hamilton's equations. 6. The Lie derivative of omega along xh is d of dh plus 0, which is 0. Hamiltonian flows are canonical, and Liouville's theorem is a corollary. 7. The bracket of f and g is omega on their Hamiltonian fields. The rate of change of f is the bracket of f with h, and energy is conserved by antisymmetry. For Lecture 8, cotangent bundles in earnest. Lecture 3's slogan that every point transformation is canonical finally gets its proof.